Hey guys, today we're going to talk about acceleration, which is another quantity that you probably have heard this term before, but may not know exactly what it means. So we're just going to get right into it. I'm going to try to keep this fairly short. I know my videos a lot of times take a while. So this is you have the PowerPoint there. I did want to do a little bell ringer just to make sure we're good on velocity. So this is a velocity problem that involves some converting. So let's look at this together. Sarah's mother is going to pick up Sarah's cell phone from the office because Sarah was caught using it during class, which is obviously not an issue that anybody has right now because, you know, you can, I guess, use your phone at home and no one's going to stop you. But we're going to pick up Sarah's cell phone, and I noticed that my Mobi's not working, so hopefully it works when I restart it because it would not be good if I have to. Yeah, it looks like it's not going to work, so I'm going to pause this and see if I can get it. Oh, never mind, sorry. Still working on this. Okay, it's working. I don't even know why it wasn't working. It just, whatever. Anyways, okay, so Sarah's mother okay, we already read the problem. Let's just jump right into it. I'm trying to find, she starts 10 kilometers south of the traffic light. It takes her 10 minutes and she ends up 5 kilometers north of traffic light. Find Sarah's mother's velocity in meters per second. Notice again, the unit here is meters per second, but a lot of the units we're given were not. So let's just set this up with a velocity is the change in displacement. Uh-oh. Man. Okay. Sorry guys, I really hope this works. I don't know why. Divided by, it's going to make me really grumpy like Oscar the Grouch if this doesn't work. The change in time. So in this case, with final displacement, where do they end up? She ends up 5 kilometers north, so that's positive 5 kilometers because it's north. Minus, she began 10 kilometers south, so that would be negative 10. And again, that minus is separate than the negative 10 kilometers. And it took her 10 minutes. All right, 5 minus negative 10 is the same thing as 5 plus positive 10, so 15 kilometers. And again, this represents her displacement. She traveled 15 kilometers north because it's positive in 10 minutes. So you could, calculate this is going to be 1.5 kilometers per minute. But of course, that's not the unit I want. I want meters per second. So then I just have to do a little converting, right? Hopefully you're used to it at this point. Minutes would go on the top. It doesn't matter which one you cancel, kilometers or minutes first. I'm going to go minutes to seconds, and I know there are 60 seconds in a minute. And let's get rid of kilometers to meters. 1 kilometer is 1,000 meters. So I'm going to take 1.5. You can cancel stuff out. I probably should. It's good to have it. Minutes cancel. Kilometers cancel. So I'm left with meters in the top and seconds in the bottom. So I know I'm done and I know I have the right answer as long as I don't, hit 2 buttons on the calculator wrong or something. 1.5 times 1,000 divided by 60. Put in my calculator, I get 25 meters per second, and that's my answer. Okay, so just want to make sure that you are comfortable with those converting, because again, it's just going to be something that we're going to stick with, that dimensional analysis stuff. All right, moving on. Normally I would do sort of I would have you really stop here and talk about a lot of different things, but again, you can pause this and think for yourself, but are you currently moving? Well, you can probably figure out that you are, of course. Your atoms are moving around, molecules are vibrating very quickly, electrons are moving around the atoms. I mean, there's tons of motion going on. You can't stop that motion, right? You can stop this atomic and intermolecular motion if you decrease the temperature. If you make it, in fact, there's a temperature where it's so cold there's no energy left. We call it temperature absolute zero. So imagine I took some object and I froze it to absolute zero. Would it still be moving? And the answer is, of course, yes. We're on Earth. Earth is, traveling through space rather quickly around the sun, and of course, the sun is moving around the Milky Way galaxy, and the Milky Way galaxy is moving itself. So there are many, many ways that we're moving, and we're moving actually very, very fast. But of course, we don't feel like it, right? I mean, I don't feel like I'm moving. I could just sit here and say, okay, feel comfortable. I don't feel like I'm right because you probably think like, well, you can tell if you're moving, but actually you can't. That's called relativity. You can't tell if you're moving. It is, if the Earth is moving, right, we know the Earth is spinning. Well, for a long time, there was this debate on whether it's, is the Earth moving or is the sky and the sun moving around the Earth? Well, of course, we know the answer today. But there's a reason why that debate raged on for so long, because it's very difficult to tell if you're moving. Well, with that in mind, how do you think you would feel here? Now, this is, I'm going to turn this sound off. This is a roller coaster. Of course, you've been on a roller coaster before. You know that. You would feel this, right? I wouldn't just like, fall asleep here on the roller coaster. I would definitely feel this. So what's going on? What's the difference here? Why on one hand am I telling you that you're not going to feel motion, but on the other, you know that you will, right? And then I'll let this play for just a second more. This actually is a roller coaster in Japan. Has a world record for being the steepest drop, not the highest drop. Okay, there's a difference. The steepest drop. So you can see here we're going to go up. I'm going to skip ahead just a little bit. So again, think about how would you feel if you were on this roller coaster. Oh, here we go. Look how steep this is. Here, I'll be here so you can see how steep it is. This might give you, sweaty palms or something just watching this, right? Woo! All right, let me skip ahead. You can see why it has the world record for the steepest drop. You can see here, so you can see it actually goes in, right? So it's not just like a 90-degree drop. It actually inverts, so it's more than 90 degrees. You slightly invert there. Pretty cool. Okay, but the point is, right, you would definitely, right, no one is questioning, you would definitely be able to feel like you're moving on that roller coaster. So what's going on here? Well, I would have you talk about it, but the answer is you're accelerating. And you can feel acceleration. Acceleration is different. And acceleration is what you feel, kind of that feeling in the pit of your stomach, when you go down a big drop, or, you're on, maybe you're driving. Maybe you're not driving probably yet, but you will be driving soon. But maybe your parents are driving and they turn too sharply. You feel that, right? You feel that acceleration. Acceleration is a change in velocity. So acceleration is a vector. You can see the equation here. You can write it down. You'll notice the equation is very, very similar, right? There's this interesting mathematical and physical relationship between all these quantities that we're talking about, right? Because we started with displacement. Displacement is just how far you move or where you are. A change in displacement with respect to time is called a velocity. And a change in velocity with respect to time is called an acceleration. So acceleration is how quickly your velocity changes. If you go on to take calculus, which I hope you do, it's a really interesting class. You learn some interesting mathematics. It was actually invented, right? Well, okay, there were two people who, it's a little ambiguous who invented it, or they co-invented it together, Leibniz and Isaac Newton. But at least it was Isaac Newton discovered it or invented it for the purpose of solving problems in physics. So, we're kind of doing watered down versions, but if you know calculus, there is this relationship where you have displacement, and velocity is the derivative of displacement with respect to time, and acceleration is the derivative of velocity with respect to time, which is just a derivative is just like an instantaneous rate of change, basically. All right, so hopefully you have that down. But here's the big question. What are the units of acceleration? I want to take just a moment to talk about this. Because once again, if we're using dimensional analysis, we can do that. We can use that to figure out the units of basically any, we can figure out the units of anything, right? So, let me get my pen here. Okay, what are the units of acceleration? So what we're going to do, the way we're going to always figure this out when we're having a unit, is we're going to take our existing units and we're going to put them in the equation, right? So it's a change in velocity divided by a change in time. Well, a change in velocity is measured as meters per second. So meters per second, that's the velocity, divided by time, the standard unit for time. And I should say we're really finding what we call the standard unit, the standard metric unit. But metric is what we obviously use in science. Divided by the change in time is going to be just seconds. So what do I get? Mathematically, how would if I take meters per second divided by seconds, what do I get? And I encourage you to try to figure this out. But if you don't remember, here's meters per second divided by seconds. Now, don't be tempted to cross those out because this isn't multiplication. It's division. How do you divide? And you put 1 on the bottom and 1, 2. How do I divide fractions? The answer is I don't know how to divide fractions. What I do know is how to take a fraction division problem and turn it into a multiplication problem, right? I think there's some kind of, I don't know, there's some saying, I think it's keep, change, flip, maybe. I don't know it. I just know that you just, meters per second, you just flip, you multiply by the reciprocal. That's the same thing as dividing, right? If I said what's 8 divided by 2, that's the same thing as 8 times the reciprocal of 2 is 1/2, and those are the exact same thing. So it's the same thing as meters per second times 1 over second. And then hopefully we can figure this out, right? Because we just multiply across the top. Meters times 1 is just meters. Seconds times seconds is second squared. So the unit, the standard unit is important for acceleration is meter per second squared. It means meter per second per second. So if I have an acceleration of 1 meter per second, what does that mean? Or sorry, 1 meter per second squared. What does that mean? It means my velocity is changing, right? It's changing by 1 meter per second every second. So if I'm going 1 meter per second, 1 second later I'm going 2 meters per second, 1 second later I'm going 3 meters per second, 1 second later I'm going 4 meters per second, and so on. It's just going to continue to get faster and faster. So what are the 3 ways that you can accelerate? I want you to think about this for a moment. The hint here is, what is acceleration? It's a change in velocity. So what are the 3 ways you can change your velocity? There should be 2 that are kind of obvious, I hope, at least. How can I change my velocity? Well, easy. I can speed up. Yeah. Great. We can speed up, go faster. If you go faster, you are definitely changing your velocity. What's the second way? Well, if I can speed up, and that's an acceleration, you can also slow down. Great. 2 different ways you can accelerate because you are changing your velocity. You're going faster, you're going slower. And think about this from the perspective of anytime there's an acceleration, we're going to find out later there's kind of a force that's associated with that. So think about this. If you speed up, is there a force that you can feel? Well, if you've ever been in like one of those catapult roller coasters, I think they're called, or whatever, where they go from like 0 to 60 in 2 seconds or 2.3 seconds, yeah, you definitely feel that, right? It's like in your chest, it's pushing you down. You definitely feel the force there of that acceleration. Same thing with slowing down. Obviously, if you've ever, hopefully this hasn't happened, if you've ever been in a wreck or close to a wreck, you immediately slow down, and that's where you feel, and that's what causes those injuries because you're accelerating so fast. But there's actually one more way that's maybe not as obvious. And remember, the key to this is when we say accelerate, really what are 3 ways you can accelerate is the same thing as what are 3 ways you can change your velocity. But remember, velocity is a vector. What do vectors have? 2 parts. Okay, recall, what do they have? Direction and magnitude. These 2 things deal with the magnitude. Really, these are changing your speed, right? Because the magnitude of velocity is speed. So they change your speed. What's the other way you can change a vector, though? What's the other part? It's direction and magnitude. So what if you just change your direction? Is that an acceleration? Change direction. The answer is yes. Even if you take the exact same speed, if you change your direction, you accelerate. And you can feel this, right? When you take a turn in a car, you're going to feel yourself push to one side as you turn, because you're changing your velocity. And that's really what roller coasters do well, right? I mean, they do speed up and slow down, but usually that really just happens when you go down a big drop or at the beginning or maybe the very end. But in the middle parts, right, you're not really changing speed that much. So why do you still feel like that thrilling sort of feeling? Well, because you're changing your direction, right? You go in a loop and you feel that. All right, let's look at a couple practice problems. I'm going to do, I think, 2, and then you will have a practice today. So again, I am going to, like I said, wrap this up pretty quick here. A car spinning down road 40 meters per second south. They notice a cop, and 0.4 seconds later, they're going 25 meters per second south. What is the acceleration of the car? Now, again, acceleration is a vector, so it's going to have a direction. It's going to have a sign. That sign is going to tell us the direction of that acceleration. Okay, acceleration is going to be the change in velocity. Let me change my pen size here. It probably didn't make any better. Change in velocity divided by change in time. This is really final velocity minus initial velocity divided by final time minus initial time. And again, we're not going to spend too much on this because it's very, very similar to velocity. If you did final velocity, you'll do final with acceleration because they're very similar to each other. There's this mathematical relationship between the two. All right, so here the final velocity, they're going at the end 25 meters per second south. That's negative 25 meters per second, minus they were going at the beginning negative 40 because it's 40 meters per second south. Got to pay attention to those negatives and positives, because if you missed the problem, that's probably why you missed it, because you just missed a sign somewhere. Divided by how long did it take them? Again, the final time here is 0.4 seconds. The initial time one we can just call 0, or you'll just find out just divided by the time, really, the change in time. All right, so on top, I have negative 25 minus negative 40, and I get positive 15. So the acceleration is 15 meters per second divided by 0.4 seconds. I didn't put my unit down there, sorry. So 15 divided by 0.4 is 37.5. That unit is meters per second squared. Now there's some interesting implications here. What is the sign that we got on this? Well, obviously it's positive. So what direction is the acceleration? Well, again, we're really only talking about north, south, or east, west. We're going to combine directions later, but for now, these are called one-dimensional problems. It's either left or right, positive or negative, up or down, north or south, whatever. So here we're talking about north and south, of course. So if we get positive 37.5, that direction is north. Now this is where it gets a little weird, right? Because we're going to talk about the relationships, right? We're talking about the relationships between different, like velocity and acceleration. You're going to see that a lot when we talk about graphing in the near future. But what we have here is, right, the acceleration is separate than velocity. So in this case, if you're moving, right, he's moving south, clearly, but he slows down. Slowing down his velocity south is sort of an increase towards the north, right? So this is actually slowing down even though we got a positive number here. Positive doesn't, so if you negative doesn't necessarily mean slowing down. Negative tells you the direction. Positive doesn't necessarily mean speeding up. Positive tells you the direction. The direction of this acceleration is north. So if he's going south, if he's going down, right? This is what I'm trying to show you. If he's going down, right, and he's going to slow down, he really has an acceleration. Acceleration you can think of almost like a force. Imagine, and there is going to be a force, right? If he's slowing down, there has to be a braking force there, and that braking force is actually pushing back up north, and that's why the acceleration is north. So he's actually accelerating north. In other words, his northern velocity is going to be increasing. Right, and so you can think of this as like a push on him. The push is going north to slow him down from going south here. And we can work on the sort of the relationships there in that direction as we go on. It's not critically important now as long as you know how to calculate it. All right, let's look at one more. A clown is attempting to go through a loop on a small bicycle. He starts from rest and after 8 seconds is moving 14 meters per second south. Find the acceleration of the bicycle in meters per second squared. All right, so once again, we're just going to start with our acceleration. I don't know if anybody's a fan of The Simpsons. I really liked The Simpsons when I was younger. I still like the early seasons, you know. I haven't watched it like anything past, I guess, season 14. But the early seasons are still, I think, really good, actually. And originally, if you care about this at all, which you probably don't, originally Homer was going to be, this is from the episode where he goes to clown college. He was originally, originally Homer was going to be Krusty the Clown. And it was sort of this thing where, like, okay, Bart hates his father, but he loves Krusty, and really they're the same person. But they scrapped that pretty early on. Okay, so acceleration is change in velocity divided by the change in time. So it's going to be Vf minus Vi divided by, and if it's okay with you, I'm just going to use change in time on the bottom. All right, so what's the final velocity? At the end, he's going negative 14 meters per second because it's 14 south. Minus at the beginning, he's at rest, so that's going to be 0 meters per second. Divided by the change in time, it takes him 8 seconds. All right, this was easy on top. Negative 14 meters per second divided by 8 seconds. Pull out your calculator. I got negative 1.75 meters per second squared, or you could say 1.75 meters per second squared south. So his velocity is increasing in the south direction. And again, that negative doesn't mean he's slowing down. It could mean he's slowing down sometimes, but in this case, the negative means it's in the south direction. So that's make sure you know that positive or negative indicates the direction only. Okay, I think that's all. You've got some practice today. Like I said, I've tried to make this short. We're like 20 minutes, so I know it's not that short, but well, it's short for me, I guess. All right. Thanks for watching. If you have questions, as always, make sure you send me an email or ask on Google Classroom or whatever it is, okay? You've got some practice questions on Schoology you look over. We're going to start talking about graphing pretty soon as well. All right? See ya.